怎么样？OK 了，我来 check 一下，我来 check 一下这。Good morning. Hello, Tokyo. Hello, Tokyo. Can you hear us?
I can hear.
You can. You can do. Hello,
Okay,
Hiroshima.
Good morning.
Good morning. Can you hear us?
Yes, I can.
Yes. Okay. All right. Okay. Let's start. Today we're finally talk about frequency and the instantaneous frequency. Everything we do is actually in preparation for this. Okay. But then after we finish this, you find that we still have problems. This actually represents a total new view of frequency. Instantaneous frequency is not new, but it is still controversial. All right. I will tell you why it is still controversial. As we said before, the physics book always define omega as 1 over t. Yeah, 1 over t means that you have to have a whole wave before you can talk about frequency. And intuitively, that sounds reasonable. That if you don't have a oscillation, a whole oscillation, how can you talk about the period? If you cannot talk about the period, how can you talk about the frequency? But if we extend this idea to the kind of derivative, then we'll find that from a differentiation point of view, like velocity is distance divided by time, but by how large a distance divided by how long a time. Okay, so we have this idea, velocity equal to ds dt. This is a new concept. ds dt is a new concept. When I read Newton and Leibniz, differential calculus is actually invented jointly by Newton, Sir Isaac Newton, and Leibniz. And at the beginning, they had a very hard time to get their paper published, because they always say ds dt becomes infinitesimal. Then people ask them, how small is infinitesimal? Yeah, they cannot really say how small is infinitesimal. Yeah, how about 0? So as a result, they propose calculus as an algorithm. So if you follow this, you will get your answer, right? But this limit concept has to come before we can truly understand the limit. This is the limit dt approach to 0. That's what it is. So if we can get velocity in terms of this, we should be able to get a frequency with 1 over period. This is very crude, and this only works for one sinusoidal wave. If I have a wave which is not sinusoidal, even though I have a 0 crossing and another 0 crossing, another 0 crossing, that still does not mean a period. So to call that a frequency, it's unfair. And it does not apply to non-stationary process. If I have a frequency wave, the period keep increasing, and you say, well, this is one period. What do you mean one period? Which period? Okay. And nonlinear process is the same. Yeah. The same period, the frequency may not really mean the same thing. Like a triangular wave and a sinusoidal wave, they may not mean the same thing. The frequency, instantaneous frequency, may not mean the same thing. And most important of all is that all this frequency definition, you cannot use it in any differential equation. Yeah. 1 over period. So with one wave is constant. With another wave we jump. So at each wave you have a jump condition. You put in differential equation, you have a lot of jumps. Okay. So all of this means that 1 over period is not very good. So how many different ways that we define frequency? So to define frequency for any data, Any data, arbitrary data you give me, I can immediately define frequency for you. How? By Fourier analysis. By Fourier analysis, then we have omega. This omega is omega over here. So this omega, however, is integral from 0 to capital T, or from minus infinity to infinity. We know we don't have minus infinity to infinity. So from 0 to T, that's our period, our total time. So this frequency definition will give you many, many, many frequency, but each frequency is constant from beginning to end. Okay? Now, if we do not use this Fourier analysis, we have wavelet. Wavelet analysis can define frequency too. Wavelet analysis, most people use wavelet analysis, do not express their result in terms of frequency, but it should be able to express as frequency. We did not cover wavelet. I thought you perhaps know something, and maybe in the future I will use, say, 1 hour or whatever, give you an introduction to wavelet. Wavelet is a transformation. It's a dilatant translation. Yeah, the dilation is actually in terms of frequency. It's a scale. Yeah. Another one is Wigner-Weil analysis. Wigner-Weil analysis, I should maybe cover that a little bit. Maybe next hour we'll talk about a little bit of Wigner-Weil. Okay. Wigner-Weil, it's actually a Fourier transformation, but it's a central correlated function and a Fourier transform. Anyway, any data, if it's from linear process, you can immediately do Fourier analysis, you can do wavelet analysis, you can do Wigner-Weil. You all get frequency. And that frequency you get, however, it's constant all over, constant over the integral region, and constant again constant over the integration period. So here's Fourier. We have already met him, so we don't have to talk about him anymore. And we know that the Fourier is constant. It's constant all the time. Yeah. The Fourier transformation has a lot of information in that. But most time when we use Fourier, we drop one of the very critical important information. That is the phase function, phase information. When we do spectrum, the spectrum is just the amplitude. It's just the imaginary plus the real, the sum. So we never really keep track of the phase. See, the phase is very important. Like, for example, if I have 5 Fourier components, depends upon how I reconstitute it. I can actually have a very different result. If I have the phase locked, you see, if I have all the Fourier component maximum all center at 2, then each component add will have a positive reinforcement. So by the end, if I add, say, 10 or 15 or whatever number of values, I will have a very large value at that phase lock point. And all the others will eventually cancel out. So the oscillation becomes smaller and smaller. However, if I have a phase randomized, then the number can be very different. So, in Fourier analysis, if I give you a delta function, and if I give you a white noise, you will have the same.
Excuse me.
Yes. So my voice.
Yeah, we cannot hear you.
I don't know what
clear.
happened.
Please check.
Let me see if I can make this better. No. Well, looks like
I can hear. Yeah, thank you.
to talk India. Okay. Just one more. Hello? Can you hear me?
Yeah, I can hear.
So no problem, Tokyo?
Yeah, no. Yeah,
No, how about Hiroshima? No problem. Okay. So now I have to glue myself to the microphone. Okay. So if we have the phase lock and not phase lock, you will see the difference. For example, this is 10 component if it's not phase lock. So we have a maximum here, and we may have maximum here. We maximum shifted over. And so when you add it up, you add it up in a random white noise. However, if you have all the maximum all located the same place, so that will give you very different thing. Therefore, in the Fourier spectrum, even though you get a frequency composition, you may not get back the signal uniquely. In other words, from spectrum to signal, there's no unique reconstruction. The reconstruction depends also on the phase. Yeah. So, and this Fourier analysis has another difficulty is that the uncertainty principle. If you want the frequency to be very nice, you have a very well-defined frequency. But you look at all the harmonics you have. You have all the harmonics to simulate the same sound, same signal. And if you do not want to have, if you want to have time more precise, then the frequency diffuse. Then even the harmonics disappear. So there is problem. There are lots of problems in Fourier analysis. Yeah. Now, the problem, in fact, the problem is not only with Fourier. The problem is with all the integral methods. Yeah. This frequency cannot be a function of time within the time integral. And that's the problem. So the frequency variation could not be found in any differential equation or differences because it's constant over the integral time. And the integral transformation pair suffers the limitation imposed by the uncertainty principle. Still, another definition of frequency is by the dynamic system by Hamiltonian. The Hamiltonian is that if you find a Hamiltonian, H equal to P, Q, T, then P and Q and T, T of course the time, P is a generalized momentum, Q is a generalized position, location. So if you find a Hamiltonian, and if you also find the action, then the action is the integral of generalized momentum with respect to generalized coordinate. And this integral make the action an average quantity. It's not a instantaneous quantity. It's actually integral over a whole cycle. Okay. So once you get the Hamiltonian and action, then the partial derivative of Hamiltonian with partial derivative of action give you a definition of frequency. So this frequency, again, is not quite instantaneous because of the action is not instantaneous. But this is a very rigorous method established in the classical mechanics frame. But this cannot be used as data analysis, because most of the data that we have, we will never be able to find a Hamiltonian, because our system, a lot of the system, is so many degree of freedoms. So this Q is going to be so many independent variables. Yeah. So this is not a data analysis method, but a system analysis method. This method, as far as I know, only works for very simple, low-dimensional dynamic system. Yeah. Now, if we go further than that, there are other methods. But when we come to the other methods, then there's a restriction. The restriction is that it no longer works for general data. Any data you give me, it doesn't work. It will only work for specific data. That specific data typically is for IMF. That is, in the past, before they know what IMF is, in the past they always say, work for narrow band. Narrow band means that you have the same number of extrema and zero crossing. Okay, and that is one of the definition of IMF. But IMF, when they a little bit further, is not only have the same number of extrema and zero crossing, and you will also have the symmetric envelopes. So the next two definition will you have to have IMFs. Before you have IMFs, it's not going to work. Yeah. Now this method, one is Tigger's energy operator. The other one is a period between zero crossing and extrema. I will explain this too. What is Tigger's energy operator? Tigger is a graduate from MIT, Nobel winners group during the Second World War. He studied the statistics, studied radar, studied the noise and all that. After that, he was a professor at the MIT, but he has a very strong opinion. So the department head said, well, listen, we want you to work on such and such problem. He said, no, that's not of my interest. So the professor, the department head politely invited him to leave. So he left. After he left, he moved just across the street to across the river to Boston College. Yeah, and he stayed all the time at Boston College. If you leave me alone, I will probably never know him, never find him. Actually, I do not know him. By the time I know of his work, he has already passed away. The reason I know him was that I know by some interesting connection, I know Jim Kaiser. Jim Kaiser is the person that invented the Kaiser window. You know, Hamming window, Kaiser window is the person invented Kaiser window. They know each. They not only know each. Kaiser not only know him. They are in-laws. They married sisters, a pair of sisters. After he passed away, Kaiser was asked to look at his paper, all his paper accumulated throughout his career, and he come across this energy operator, and he liked it very much for some reason. And then when I met Kaiser, Kaiser insists that I made a comparison of EMD and Hilbert transformation with the energy operator. Excuse me. So I dug up Tigger's paper and started to read it. And the idea is very simple. The idea is if you have any variable x, you define an operator called psi c. The operator idea is, you know, the double E people always use operators. Okay, you operate on xt. What is this operator defined? The operator defines that if you have any variable, I will take that variable, take the one-time differentiation and square it. And then minus that the second time derivative, multiply by itself. This is x dot square minus x double dot times x. That's the operator. What does this mean? This actually exactly means energy. Why? Because x dot, if x is position, x dot is velocity. So this is velocity square. And x double dot is acceleration. Acceleration means force. Acceleration times displacement is potential energy. And the minus sign is that if it's sinusoidal function, second derivative gives you a minus sign. So if you minus, that means plus. That means energy, kinetic energy plus potential energy is total energy. Okay? So this means total energy. Yeah. So this is total energy. For example, if xt equal to a sine omega t, if we take x equal a sine omega t, we put in that operator. This x dot is a cosine, a omega cosine. X double dot is a omega square sine. Sine times sine, sine square plus sine square is 1. So it's a square omega square. Okay, so this total energy is a square omega square. All right. Then, if Tigger then thought, wow, if we have such a nice property, why don't we also operate on x dot? If we operate on x dot, you see, this x dot then becomes x double dot. This then becomes x triple dot. So by introduce the x dot in here, you get an extra omega. So if you operate on x, you get omega a square omega square, and you get operate this, you get a square omega fourth. Well then we have interesting situation. That is, if I divide this by that and take square root, I get omega. And I divide if I divide this square root of this, divide into that, I get amplitude. Yeah. It sounds great, but you have to realize this works only when a and omega are constant. That means the data is very, very restricted. Yeah. That means amplitude cannot change, frequency cannot change. It works perfect for sine wave. If I have a sine wave, I don't have to go through this to get frequency. Right? Right. So this works, but it works only approximately. Yeah. And I will show you how poor it performs when it's not approximate. Okay. So this is the Tigger's energy operator. I was forced to look at this, and I was forced to make comparisons. And by forcing me to make comparisons, I also find some mistake of my own. So that it was a very good exercise in going through this whole comparison. The next one is so-called generalized zero crossing. Who have waves? 1 over t is period. 1 over period. T is period. So that is actually zero crossing. But I think when people doing zero crossing, zero crossing is a very good measure in the mean of the period. But if we want to know the local frequency, we use period. Zero crossing, it's too crude, as we have already said. So I propose a generalized zero crossing. What's generalized zero crossing is that if I have data like this, then I first define the critical points. The critical points are the points that the x equal to 0 or x prime equal to 0. So I identify all the zeros, zero crossings, and also all the extremas. Yeah. So once I identify all the zeros and all the extremas, then I draw lines through this. Then I will see that from here to here is one time. From here to here may be different. From here to here still may be different. So the spacing from the critical points one to the next are very different, one from another. So they represent a certain degree of locality. Then if I measure another way, I measure zero crossing to zero crossing, or extrema maximum to minimum, or down zero crossing to up zero crossing, or minimum to maximum. So I have another set of measurements. And these measurements, again, is different from different. In other words, I skip one, I measure this, measure that distance. Each distance value is actually different from the other, from other values. Then the third way to measure that is from maximum to maximum, from minimum to minimum, from minimum to minimum, from up zero crossing to up zero crossing. Now this is a whole period, from maximum to maximum, from zero crossing to zero crossing, up zero crossing to down zero crossing, from minimum to minimum, from down zero crossing to down zero crossing. You see, this distance again are not the same. Not only they are not the same, if I pick up any point, for example, I pick up any point, I have very different values. Depends upon I read here or I read here. If I read here, I get this value, or I can get that value. And I come down here, I get 4 values. So which value should I use? So that becomes a problem. So the generalized zero crossing is that I consider everything. I consider everything. If I use T1, which is T1 is this. So this one is the most local because it does not involve the wave beyond this particular quarter phase. This one is also local and is beyond the half wavelength. And this one is only for one wavelength. So this is the most local. This is less local. This is the most universal or spread out. So what I did is that if I use T1, 4 times T1 is my frequency, should be. If I use T2, 2 times T2 should be my frequency. If I use T4, 1 over T4 should be my frequency. But I think because this is very local and this is not as local, so I will assign a little bit weight to it. So arbitrarily, to make the final result simpler, I just assign a factor of 4 for this, factor 2 for that, factor 1 for this. The factor 4 for this is 4 times F1, it's actually 1 over T1. 2 times F2 is 1 over T2. And then 1 over T4. You sum all this up and you divide the total weight. And that is your mean frequency. So this is the generalized zero crossing. So once we have this, you will know that the TEO has a super time resolution. There's no method has a better time resolution than TEO, because TEO involves that point and the second derivative at that point. And the third derivative actually involves 4 points, 4 neighboring points. You can get the TEO. So the Tiger energy operator is super time, has a super time resolution, but it is strictly for linear process. You have to be constant amplitude, constant frequency. If it's not constant amplitude, not constant frequency, you'll have all kinds of problems. Now, generalized zero crossing is not very local. It's crude, but it's robust. You cannot make it wrong very far. And not only that, any value you got for frequency, if the mean deviate from generalized zero crossing, it has to be wrong. Yeah, because 1 over t with all the negative properties, but it is the mean by definition. And if you get a value and the average value is not that, then it cannot be right. So we have two methods. One is very, very local. The other is very robust. Yeah. So I actually use this a lot to serve as a reference. If my value come out to be dramatically different from that, I know it's wrong. Yeah. But this one, this value is hard to use. Even its localized property is hard to use. Now beyond that is the Hilbert transformation. Yeah. The Hilbert transformation, again, used only for IMF. That's using Hilbert transformation, we get the theta, the omega can be defined as time derivative of theta. Still, another variation of that is called quadrature. The word quadrature in English has a lot of different meanings. The method for computation, method for integral, and all that. Here, the quadrature will strictly mean that you take a value, you shift it to 90 degrees, and then compute arctangent. How to shift the value becomes that. So you get your value, you get your x, and this x is actually IMF. You normalize x to be 1, magnitude to be 1, every peak to be 1. Then 1 minus x squared gives you y, which is this is sine, then you get a cosine. If this is cosine, you get your sine. Then sine, cosine, arctangent give you theta, and dt d theta give you that. So this is called the quadrature method. Okay, so we'll see how each method works. Having talked about instantaneous frequency, I have to talk about these two quotations. This, in a way, still represent some views in the community. The first is a relatively old view. In 1953, Shekl said the term instantaneous frequency should be banished forever from the dictionary of communication engineer. Luckily, he said communication engineer means other people can still use it. But the language so strong means that this is rubbish, this is nonsense. Instantaneous frequency should not be used at all. Now that's 1953. 2001, a mathematician come up, and he wrote a book called Hilbert Transformation in Mathematical Foundation for Hilbert Transformation, or something like that, or Mathematical Foundation for Time Frequency Analysis. I'm sorry. Now, what he said in that book at the beginning is that the uncertainty principle makes the concept of instantaneous frequency impossible. And let me translate this. What he said that if you cannot make time absolute or frequency absolute, how can you make a frequency instantaneous? Because you never know exactly where it is. You never know exact what the time is, or never know exact what the frequency value is. So there's nonsense. It's impossible to talk about instantaneous frequency. The problem with this statement is that his whole book is based on Fourier transformation. Yeah, if you use Fourier transformation, instantaneous frequency is impossible because of the uncertainty principle. You cannot pin down the time arbitrarily close and the frequency arbitrarily close at the same time. When you pin down the time, frequency smeared. When you pin down frequency, time smeared. So what is instantaneous frequency? Nothing. Okay. So if you stick to Fourier analysis, this is true. If you stick to any integral transformation, this is true. But if you escrow the Fourier transformation, escrow any instantaneous, any integral transformation, this is not true. Yeah. I cannot talk about this guy. This guy obviously has ideological differences. It's beyond argue. But this we can argue reasonably. There's no reason. This is just banish it. Talk like a dictator rather than like a scientist. Now, so the ideal case of instantaneous frequency is that if we obtain an analytical signal based on real value functions through Hilbert transformation, if we have IMF, yeah, and IMF is a real value, and we use Hilbert transformation, we get the analytical signal. And using that, we compute the instantaneous frequency by taking derivative of phase function of the analytical value. We thought that should be the end of the problem. But this is not true, it turns out. This is true only if the function is an IMF and its imaginary part of the analytic is identical to the quadrature of the real part. Unfortunately, this is only true for very special and very simple value function. Yeah. So taking IMF and making Hilbert transformation, going through this route, there's no guarantee that you will get your instantaneous frequency. What happened is that the limitations, data must be in IMF, which is given. Okay? But IMF is only necessary but not sufficient. If it's not IMF, you can forget about it. If it's IMF, it's not necessarily true. Why? There are two mathematical theories in our way. These two mathematical theories, one is Bedresin theory. Bedresin theory is Hilbert transformation of A cosine theta may not be exactly A sine theta. Why? You see, A cosine theta, A sine theta, A is not involved in the transformation. When we do Hilbert transformation of this, we say, okay, A can just stay out, cosine theta becomes sine theta. That's the implication. Now, for Hilbert transformation of A cosine theta to be A sine theta, the spectrum of A and the cosine theta must be disjoint. This is what the Bedresin theory says. I will later get in a little bit more detail. By the way, I posted on the web a big folder of mathematical preliminary backgrounds. And I will not be able to go through that for this class, especially for our classmates from Tokyo and from Hiroshima, because by the end of November, your class will be over. Those mathematical preliminary was part of my lecture last year. Yeah, I will just put it there for you to enjoy during your winter vacation. Okay, I'm not going to cover it. So in there, you will see a lot of detailed proof of some of the theory that I'm talking about. Okay, but now you have to trust me. So what the Bedresin theory says that the A cosine and A sine, only if A and the cosine, their spectrum are totally separate. In other words, the A is very low frequency and cosine theta is very high. The carrier is very high and it's very low. So has to be totally disjoint. Then after he published that paper, another gentleman come up, Nato. Nato said, well, hold it. Say, the Hilbert transformation of cosine theta may not be sine theta. So even if you drop the A, still does not work. not necessarily work. So this is really is the crunch of our problem. Dr. Nato, again, is from that Nobel winners group from MIT. After he finished his PhD from MIT, he joined the Navy, and he wrote profusely on data analysis. Most of the work is classified. Yeah, so he is not very well known outside, but he's very well known in the community. Yeah, I have chance. I was invited by the Navy to give a talk in the underwater system command laboratories in Connecticut. I know NATO was there. So when they invite me, I say, well, I have one condition. If I go up there, I want to meet with Professor Nato, Dr. Nato. He said, oh, no problem. You come up here. He's here every day. You can come. So I was fully prepared to meet him. But a week before my talk, they called me. They said, unfortunately, he had a heart attack. Not non-fatal. So he got rushed into hospital to have a bypass. Yeah. So I never met him. He must be a very, very interesting person, but I have never met him. What he brought up is that if you have a cosine theta, you do Hilbert transformation, it may not be sine theta. So even this, in other words, he improved upon Bedressian. Now, that gives us a lot of problem. Yeah, that means Hilbert transformation may not work very well. Yeah, so that's why it forced me into the quadrature approach. Okay, so for example, this function, we have seen this, and Hilbert transformation is that. Of course, we know that the Hilbert transformation of that, you take a differentiation. The frequency, still you have frequency, but frequency doesn't mean anything. It has a lot of negative value, has a lot of big up and down. So the need of this, for us is to decompose this into IMF. Now, the IMF, even after you get the IMF is only necessary. This is the detailed statement. This is the statement as given by Bedressian in his 1963. So what is it? Let fx and gx denote the general complex function in L2 space. Okay. If Fourier transformation of Fourier transform f omega, capital F of f, omega is larger than a, and the Fourier transformation g of this vanish for omega less than a. In other words, a f vanish for omega larger than a, so f is small but low frequency, and g vanish for a less than that, so g is high frequency. So then, when you have product fx times gx, Hilbert transformation of that, then you can take the f out and only perform frequency on g of x. That's so Bedressian theory is correct. He said that if this frequency are disjoint, you can take this f out. You only perform the frequency on the higher, perform Hilbert transformation on the high frequency component. Whether that high frequency component cosine is sine or sine is cosine, he didn't say. He just said that you can take this f out. Okay. And what Nato says is that for any function xt, the quadrature of the xt is xq. Quadrature means 90-degree shift. Okay. And the Hilbert transformation is xh. xh and x cubed minus xh squared integral from 0 to infinity is not 0, provided there is no spillover to the negative frequency part. So these two, this equation go beyond, this theory goes beyond the Bedressian. But it's beautiful theory, but it's useless. The reason is that the error is expressed as FQ. Q is quadrature. So if I know the quadrature, I don't have any problem. I will just go use the quadrature. If I don't know the quadrature, of course I don't know the spectrum of the quadrature. So this error bound is unevaluable. You cannot evaluate because you don't know this. Yeah. So our problem is data not necessarily IMF. Even if we use EMD, IMF is only necessary condition. Then we have Bedressian theory, and I have Nato theory. Yeah. Now, the discrepancy, however, is given in terms of quadrature spectrum, which is unknown. Therefore, it cannot be evaluated. So Nato theory provides a constant limit, not a function of time. So what is the error? Error is integral from 0 to infinity. Yeah. And how's that going to help me? Yeah. Do I know which exactly the place is wrong? I don't. Yeah. Therefore, it's not very useful. Not useful, not practical. So now, so our route is this. If I have X, I can use Hilbert transformation to get Y. Yeah, the X and Y combine to get Z. Now, other way, if I have X, I'll find this quadrature. But finding quadrature is a problem. There's no general way to find a quadrature of an arbitrary function of X. Yeah, so this is no general way. Now, the difference, what is the difference between these two routes? The difference is that if you go from X to Hilbert transformation to get Y, and X, Y give you Z, the analytical function, X plus Y squared does not equal to 1. Okay, so the X squared plus Y squared is not necessarily 1. In other words, this Z is not a unit vector. X plus Y, if X plus Y is not 1, then they are not, the arctangent doesn't work. So this would only be approximation. If you go through this route, X, and you find the quadrature, then if that Y of the quadrature Y, and that X and Y is exactly 1. Quadrature means if you have sine, I have to find the cosine. So then the X squared plus Y squared is exact 1. So then that phase function will be exactly a true phase. But the problem is we don't have a general method to get it. So here I summarize the dilemma that we are now. And I will show you the way that we get around this, to normalize. The normalization is to overcome the limitation imposed by Bedressian. Only by Bedressian. How to do that? We need method to reduce data to intrinsic mode function. Then we also need a method for AM FM decomposition. Once I get IMF, the IMF is a generalized function. How can I divide this generalized function into AM and FM clearly, uniquely? If I can divide this into AM, that's amplitude, FM, that's only frequency. That's FM. FM means the amplitude is 1. This amplitude is controlled by here. If I can do the FM, AM separation, then I have no problem with Bedressian. The only thing that I have to deal with is to deal with Nato. Here, for example, here is a function, a step function. I've given this example in my original paper before. But the original paper, the amplitude change is not so dramatic. And there's also a frequency change. Here, I don't do frequency change. The frequency is constant. Yeah, only amplitude change. Now, I expect to get, if I do Hilbert transformation or Hilbert spectral analysis, I expect to get a constant frequency. But look at what I got. First is that the carrier, as I said, is a single function. So it's single spike. But the envelope is a step function. Now, the step function has a very broad spectrum. So these two spectrum is not disjoint. By disjoint means there at certain frequencies only this spectrum, at another frequency only this spectrum. Here, at this given frequency, we have both carrier and envelope. So we obviously violate Bajrasian theory. Now let's see what's the consequence. The consequence is the spectrum look like this. The frequency is very nice here. The frequency looks so ugly over here. It's impossible to get a Hilbert transformation. In other words, if you got this value, it's this function, which is already IMF. If you want to use Hilbert transformation to get the spectrum, and this is what you got. It looks very bad. Many people find this and start to ask me, say, oh, what happened? What happened? So they have to wait until I publish this this paper. I'm now giving you what I present here is a paper that's to appear next year. So this is a very ugly Hilbert spectrum. Yeah. Not only this is ugly, this compare poorly with even wavelet. See, wavelet give you a very nice frequency. Yeah. And how come your Hilbert spectrum cannot even compare with wavelet? And not only that, even compare poorly with Fourier. This is a Fourier spectrograph. Fourier says frequency. Yeah. So this is a total failure of Hilbert spectrum analysis. Yeah. I was forced to find out this by Kaiser because he want me to make a detailed comparison with whoops, what happened? Yeah. So this compare poorly with all the method. However, if I normalize it, then there's no problem. This frequency is constant. Yeah. So obviously, if there's any amplitude change at all, the Fourier spectrum for envelope and the carrier cannot be separate. So suppose I have a sine function. Okay. On the sine function, only one sine, the peak of one sine function, I have a spike coming up. It's all sine function. I have one sine function has a spike coming up. So my envelope will be constant, and the small delta and constant. So what is the spectrum of the of this envelope? The spectrum of the envelope will be a delta function, right? Delta function is white, so it has frequency everywhere. So even for that simple value, we already violate. There's no way we can get it wrong. The Bajrasian theory limitation. So this is Bajrasian theory. Looks innocent, but the restriction is very, very strong. Yeah. So now that is the drastic change of amplitude produce drastically deteriorating results. If the envelope fluctuates, and the result is only really going to look poor, like what I just shown you. Yeah. Now, if we cannot separate the envelope and the carrier, the analytic signal through Hilbert transformation will not give you the phase function, and therefore the instantaneous frequency computed through such will cease to have full physical meaning. So we have to overcome this. To overcome this, we use normalization. Yeah. these are the steps of normalization. Because there's too many words, let's first skip it, okay? And I will show you how I did it, and then we'll come back to read it. This is my IMF. Yeah. Obviously, the envelope fluctuates quite a bit, right? So, in this envelope, I first take the absolute value of the data. In other words, I take the negative value and make it to positive value. So this is the absolute value of the data. On the absolute value of the data, I identify all the extremas, maximums. Then I connected all the maximum with a spline. All right. Then I divide the data by the envelope. See, the X data, this is my data. I divide this data by the envelope. And what that means? That means all the maximum becomes 1. Right? And if that doesn't work, I can take this F, I divide it by another envelope. And if that doesn't work, I can keep on doing this. I just keep doing this envelope, keep dividing by the envelope, keep dividing envelope. Eventually, this Ft will have all the maximum equal to 1. So then this will be the FM signal of my data. And what is AM? AM is all this. This is my amplitude. Yeah. This definition, you can do it any number of times, it's the same. Yeah. So let's see. This here, this is the original data plotted in a different scale. Then I normalize it once. I get a few points that maximum is still larger than 1. How can I get maximum larger than 1? Because the spline goes through the maximum, but may cut through the data, cut in the data. So the part that is undercut by the spline actually becomes larger than 1. Okay. Anytime you have that, means that you have amplitude pretty small. Yeah, you only have a small. Typically, when the large amplitude, you don't have that problem, but you may have that, but it's rare. So that's the first part, first round. The first round, obviously, I have problems over there, so I do it twice. The second time I get this, carrier, and the carrier is everything's 1. Okay. Now, original data, I normalize it once, normalize twice. I stop. That's good enough. So once I get normalized, now let's see. This is the data. This is the instantaneous frequency I got from Hilbert transformation. If I have the IMF, it's aha, that's what I got. All right, IMF, I got that. And what you see is that the frequency jump all the way, everywhere. But if I normalize it, then the frequency no longer goes negative. They all stay positive. So normalization really worked. Yeah. Now, how come I did not spot this? In fact, the problem, once you violate Bedrosian theory, one of the problems is that you still get negative value. I thought at the beginning, is once I get IMF, I will never get negative value. But turns out, once you violate Bedrosian theory, you still will get negative value. But in my original work, I have a confession. I don't know how to write programs. So I only have ideas. So when I have an idea, I ask back other people to write program for me. This programmer that I had was a very capable guy. He got his PhD from University of Paris. So sure, he wrote me a program. And when I use it, I never find a negative frequency. Only when I was forced to make a comparison with the energy operator, I found my programmer put an absolute value sign in front of all the derivative. Yeah, of course, absolute value is never negative. Turns out I have a lot of negative value, and all the negative value are all appeared in amplitude very small. And when I plot this spectrum, small amplitude does not appear, doesn't show up. So I never solved my problem. Yeah. So here you see that by simple normalization, it already drastically improved the value. In other words, if we get rid of bidirectional theory, we are already getting a very good result. Not only that, this is your original Hilbert transformation from original data. This is the Hilbert transformation of the normalized data. What is the difference? The difference is here. When you have small amplitude, and sometimes this turning around is the Hilbert transformation because 1/t. It was not taking care of every extrema. So it skipped over extrema. And so that particular value, instead of go all around 0, it make a loop here. Once you make a loop here, you get a negative value. Yeah. So this is the difference. This is the data. This is the normalized data. The phase value is so drastically different. Yeah. And when you have the when you have the normalized value x, of course you can get a Hilbert transformation, you get y. Yeah. Because x is unit. Y, if y is strictly quadrature, it should also be unit. So x plus y should be 1. Now here we plot x plus y minus 1. See whether it's 1. It's not. See, there are a lot of places that has high values. Yeah. So this value is our error bound. This error bound is much better than the mathematically derived error bound by Nato. Nato is a uniform bound. It's not a function of time. Here, our error bound is function of time. See, over here, the x and its Hilbert transformation, the sum of that minus 1 is very large. It's about more than 25%. So what do you look? Here you look, you find that over here you have a very large deviation. Over here you have very large deviation. Over here you have large deviation. So everywhere you have large deviation are all the places when the waveform locally deformed. So this leads me to believe that Hilbert transformation is a linear operator, and therefore it only works for linear functions. For nonlinear function, it offers only approximation. So Hilbert spectrum is an approximation, and this leads me to believe that all the large values are all related to the functional form that has small distortions. Yeah. But nevertheless, we know where it's wrong, where we may have errors. Yeah. So let's skip this part. So this is the way that we did. First, we obtain IMF. Yeah. Then find the local maximum of absolute value of IMF. So take the absolute value. Okay? And then construct a spline envelope. Yeah. Then when the envelope goes under the data, then we here we say straight line envelope will be used. You don't have to do that, and that's fine. Just let it go through this. Yeah, and then this will the normalized data is data divided by the spline envelope. Yeah, and this step can be repeated. We can repeat once, repeat twice, repeat until we have it right. Then compute the IF, instantaneous frequency from FM, and compute the absolute value from Hilbert transformation data. Then the error index is the absolute value minus 1 squared. The absolute value may not be 1. It can be more than 1, can be less than 1. Okay, but whatever, if it's not 1, it's not right. The only time that the frequency is correct is when the real and imaginary part are actually exact quadratures. Yeah. So if it's a quadrature, then the absolute value from Hilbert transformation has to be 1. But as I said, Hilbert transformation only guarantee an analytic. It did not guarantee quadrature. So this sum of the real and the imaginary part, even if you normalize it, still not be 1. But this error bound is actually a function of time. So we have improved Nato's theory by provide a time-dependent bound. We know exactly where we can tolerate and where we cannot tolerate. Okay. Then once you have that, then you can compute the instantaneous frequency for the AM part. So now we have FM and AM. So we totally separate the signal into 2 components, FM and AM. But most of the time, we don't do this. Most of the time, we just stop it here once you get the FM part. Yeah. The AM is expressed as as the color bars. So let's look at some examples. Yeah. Here's the example of exponential function times cosine cubic chirp, and the data is huge coming down like this. So this is our data. We want to compute the frequency, instantaneous frequency of that. Now, if you draw a spline through maximum, this is what the spline looks like. The spline goes through maximum, but it is cut under the data. So when you do normalization, you are going to miss this part, of course. Now, immediately people suggest that why don't you use Hilbert to do normalization? So I will show you what the Hilbert transformation, the amplitude obtained from Hilbert transformation. If you do Hilbert transformation, this is the amplitude you get from Hilbert transformation. And the beginning and the end, because the Hilbert transformation using Fourier transformation, so beginning and end are the same. Therefore, this side start to tilt up. Okay, so this is the Hilbert envelope. And if you use this to normalize the data, you see the normalization over this side is not very good at all, because the value is so big. We divide into that, it's so small, so it's not normalized. But this side is normalized. But however, this normalized to make the wave skewed, the head tilted. Why? Because the maximum is here, the minimum is here. So when you divide into this, then this may become the maximum. Yeah, and this may not become the maximum anymore. So the wave, the waves after normalization, they're all tilted. See, this one's tilted, this one's tilted. This wave is no longer at the maximum. This line is the first one normalization using the spline. You can see the maximum is still a little bit bigger, but you go another time, it will come down. However, we also have a problem, because once you go through that, this peak is again not at the right peak, because this undercut over here, so the maximum now was shifted. So no matter what we do, we will miss the data. We will get only approximation, will not get exact. Yeah. So this is the kind of details that you want to see. Yeah. Once you get that, you see that the original Hilbert transformation, the phase function looks from very small and eventually becomes very large. So it's covered the whole phase space. But once you normalize it, it becomes the red curve. It's over here. That looks pretty decent. But is that correct? No, because the real quadrature of that, see here, I have the function. What is the quadrature of this? I change the cosine to sine. Right? So if I change cosine to sine, I immediately get that. And once I get that, then I normalize it, I take that equal to 1. Yeah. So this cosine plus sine equal to 1. So the curvature, the quadrature phase function is a perfect circle given by this. So a perfect circle will recover exactly the correct frequency. Yeah. So now we have to normalize the Hilbert transformation. We have quadrature. We have Hilbert, and you look at the instantaneous frequency. Now you will see that if I only use Hilbert, this is what I got. I will come out pretty reasonable, and I have a jump, another jump, another jump, and not only that, I drop down and become 0 and fluctuate all over the place. That is what the Hilbert transformation will give you. And that means that the Hilbert transformation alone, even with this function, is not going to give you the correct instantaneous frequency. Not only that, it will give you some negative value, which we say that we try to avoid by introduce IMF. But this is already IMF. We cannot avoid that problem. So this problem is very, very severe. Now, if we use this is a Hilbert transformation. Now, if we use Hilbert transformation to normalize it, what's the result? The result is here. It gets improved a little bit. You see, the large becomes smaller. Using Hilbert transformation to normalize it is smaller. And this negative becomes positive, but it becomes a large positive. And but here, I get a drastic negative value and also negative value. So using Hilbert transformation alone to normalize it is not a good approach. So, because why? Because the Hilbert transformation itself, it's more like a linear approximation, and it cannot take care of all the nonlinear shifts. So now let's look at the other one. Let's look at the generalized zero crossing. The generalized zero crossing gives a step function, step function, step function, step function, step function. This step function is almost exactly the truth, except it is steps. So any value does not go along with this cannot be right. So the step function looks very good. Yeah. And then finally, we look at the Tiger energy operator. Tiger energy operator works amazingly good for this case. Yeah. You see this Tiger energy operator is right over there. Yeah. but the only bad part is tilted up at the origin. And if we use the spline normalization, like I proposed, spline normalization amplitude, it gives you this value which goes right along the correct value, but it's oscillated slightly over there. So from this comparison, we can draw a conclusion that is whichever data over here I can use probably with I feel pretty comfortable using it. That is generalized zero crossing Tiger and normalized amplitude with spline. But for Tiger energy operator, the jury is still out. Here is the error function. Yeah, error function is that the real part and the imaginary part sum -1. Okay, if we use Hilbert transform to normalize it, our error is very, very large. Yeah, if you use normalized amplitude, the error is relatively small. Yeah, so now quadrature. We know now that the Hilbert transformation is only approximation. And what is the quadrature? Quadrature is different from Hilbert transformation. Now, to overcome the difficulty state in the Nato theory, we have to use quadrature. The quadrature is this. Let's say, for example, x equal to omega plus 0.3 sine 2 omega. This is the typical example I've used many, many times. Now, this will give you harmonics. Here, I have several lines. The first one is data. The data is sharp crested and sharp trough. Okay. The second line is this line. This line is the this line is the quadrature, because I have cosine, so I change the cosine to sine. Change cosine to sine gives me this. The value here plus value here squared. Square of this plus square of this is constant, is 1 all the time. Because by definition, cosine plus sine, whatever the function inside the function is, I don't care. It has to be sine. But if you use Hilbert transformation, you get this value. This value, you add square of this and square of that. It's not always 1. So quadrature is very different from from the Hilbert transformation. The amplitude difference is very large. Yeah. Now, if I plotted the amplitude, the quadrature amplitude, as I said, is 1, constant 1. It's no problem. Yeah. However, if I plot the Hilbert amplitude, the Hilbert amplitude goes like this. Because the Hilbert transformation, the sum is not always 1. It's only 1 at certain location, but most time it's not 1. Okay. Now previously we say that hey, the general Tiger's energy operator looks good. Let's check Tiger's energy operator, what the amplitude give us. The Tiger's energy operator give amplitude like this. There's only 1 point is right. Most of the time it's totally wrong. This is Tiger energy operator. Yeah. So now we see that once our data becomes nonlinear, Tiger's energy operator is definitely out. We cannot use it at all. Yeah. And you can use Hilbert, which give you pretty good approximation, but the best way, of course, is quadrature. Now let's look at the phase. The Hilbert transformation, because the amplitude is different, there are only 2 points, the amplitude is 1. So that's 2 points here. The rest of the time, the Hilbert transformation does not give you the correct amplitude. But if you use quadrature, the quadrature is perfect full circle. Yeah. Only when you have a full circle, then y over x arctangent will recover the full phase function. Otherwise, the phase function is not correct. Okay. Now, if we use this to compute the frequency, what do you got? You got the frequency is, this is the truth. That is the true frequency that you got from the quadrature, or true frequency you got from the formula, from the model. And this is what you got from Hilbert's transformation. It's there. It shows the oscillation, but it does not show the depth of the modulation that we're looking for. And I have pointed out this in my original paper. I say I got this fluctuation right, but I don't get the value right. I don't know why. Yeah, and now we know why. The reason is that the Hilbert transformation will not give you the exact value. The Hilbert transformation, the counterpart, will never give you the quadrature, exact quadrature. And the limitation is given by the Noether theory. Yeah, but unfortunately the Noether theory gives you uniform bound. And here, now we get, instead of uniform bound, we get the time vary bound. And this is the instantaneous frequency obtained from the energy operator. The energy operator, after I compare it, I recommend that nobody touch it. Yeah. But the energy operator, if you look at the literature, it enjoyed a few years of glory. The few years of glory was that Jim Kaiser, after he found out the energy operator, he got very excited. Jim Kaiser is a very famous guy in data analysis. He works at Bell Lab. Yeah, Bell Lab, of course, is the place to talk about signal analysis. Yeah, so he immediately uses influence. He find Professor Quantiari from MIT, Professor Menagos at Harvard. Yeah, so from MIT, from Harvard, from Bell Lab, 3 of them wrote 2 papers in the IEEE transaction, talk about energy operator. At that time, I really think it's premature, but the 3 of them, nobody can stop them. It is from MIT, from Harvard, from Bell Lab. Who's going to say no to you? So the 2 very long papers get published. Yeah. And at that time, there's no IMF. So arbitrary function cannot use this at all, period. Okay? So they use a bunch of model the function and publish a paper and say, well, this looks good. Every case is linear. Okay, it's absolutely no rigorous control test at all. No real test on data. Once I got this result, I showed to Tiger, not Tiger, showed to Kaiser. Kaiser decided not to talk about Tiger anymore. Yeah. Now here is another line. That line is this line. This line is generalized zero crossing. Okay, it looks so bad that all the other has a fluctuation and this one does not. But it's actually, if you think, actually it's not that bad because this is the mean value. Yeah. This say that you see our data our data looks like this. Now no matter which, because the data is so symmetric, no matter how you measure, you can measure peak to peak, trough to trough, upper to up zero crossing to down zero crossing, whatever you measure, the value is constant. So you get this is such a periodical function, so the frequency is constant. Therefore, you get a constant frequency. Now, constant frequency means this is the mean. So you can fluctuate up and fluctuate down. The mean has to be that. So the generalized zero crossing is still hanging there. Still a very good value. And besides, when we do data, most of the time, because of the volume of the data, you don't do instantaneous frequency of every point. When you plot Hilbert spectrum, you plot the instantaneous frequency of, say, every 10 points or every 5 points. And by then, the value is already mean value. So by then, you will never be able to tell the difference of whatever method you got. You will never be able to tell the difference from the generalized zero crossing. Yeah. So even though the generalized zero crossing seems to be so crude, seems to be so intuitive, but it's physically sound, and it's very good. Very good. It's always to give you the mean value. So I use it a lot. Not only that, this by itself gives you the standard deviation, because you get what? You get 7 different values. Yeah, and and then you get a mean, you get a standard deviation. So you know how far away from the mean that you deviate from it. So this actually turns out to be a very, very good mean value for the data. Now, if you use quadrature, of course, quadrature give you exact this. So quadrature is the truth, give you the truth. The procedure of quadrature, let's talk about this procedure of quadrature next time. So here, we have compared the truth and the normalized Hilbert transformation, Tigers operator, and generalized zero crossing. Yeah. Next time, we'll talk about quadrature. But I've already told you quadrature how to do it. The quadrature is very, very simple, and you should be able to do it relatively easily. Yeah. But is there a problem for quadrature? Of course. We'll talk about that next time. Well, thank you very much. We'll stop here today. Any questions?
Thank you.
Any questions? Hi.
Okay.
This, I presume I'm seeing Tokyo, right? All right. Any questions about the instantaneous frequency I talked about today? All right. If there's no question, the class is dismissed. I'll meet you next time on Friday. Right. Okay. Bye bye.
Okay, thank you.
Thank you.
Bye-bye.
Bye-bye.
Thank you.